Lecture 6.3 is on the Runge Kutta method, and what we're going to cover today is second order and fourth order Runge Kutta methods. The format for this method is similar to what we saw before. We start with yi plus 1, and it's equal to the initial value, plus, instead of the slope, now we're using something called the increment function, multiplied by the step size. So in this case, this increment function is equal to a bunch of constants, this a1, a2, and so on, multiplied by these variables called k1, k2, and so on. So for second order, we're only using two of these. For fourth order, we're going to add another two. So a1, a2 for a specific method, and so on, a3 and a4, are typically just constants, while k1 and k2 and so on are a function of the ODE, or the derivative that we're trying to solve using. So k1 is simply the slope at the initial condition. So now, instead of writing, dy by dt, which is what we've been writing before, I'm just going to use the letter f to represent dy by dt. So in this case, f ti yi is the same as dy by dt ti yi. K2, so that's the second variable there in this increment function, is going to be a function of k1. So we're going to take this k1 and plug it in there at a time step, which is p1 times h. So this time step also, this p1 and q11 are actually variables that we will solve for if we're coming up with a method. Basically, there are other sets of constants for a specific method. What we're going to see today is that, in fact, the midpoint method and the modified Euler's method are both second-order Runge Kutta methods. So we're going to do those first, and then we'll move on to the fourth order. So in terms of the second order, so let's start off with the general equation for the second order. So second order Runge Kutta. Looking at the equation that we have up here, what do you think is the general equation for the second order Runge Kutta? So we go up to k2, right? So the increment function is going to be equal to this. So what we're going to do is just plug that in here. Okay, so let's write that down. So we have yi plus 1 equals to yi plus increment function, which is a1, k1, plus a2, k2 times h, where k1 is equal to the derivative at the initial point, so ti yi, and then k2 is going to equal to the derivative at ti plus h, or plus p1, sorry, p1h, and yi plus q11 times k1 times h. So now a1 and a2, p1 and q11, or q11, are constants that we need to determine what they are, and they have a relationship between each other. So what do you think is the relationship between a1 and a2 are? Looking at what we've done already from the modified Euler's method. They're equal to 1, right? So a1 plus a2 is equal to 1. Then we have the relationship a2 p1 is equal to half. And then a2 times q11 is also equal to half. So you can see from that p1 and q11 are actually equal. So what's the common variable here in all three equations? a2, right? So it's present in all of the equations. So what we're going to have to do is basically give a value to a2 and then solve for the other variables. Why? Because we have 3 equations and how many unknowns? We have 4 unknowns, right? A1, A2, P1, Q11. So 4 unknowns, and that's why we need to pick one and then solve for the rest, okay? So from this, you pick one, solve for others, and in this case, you know, we're gonna pick basically A2. So if A2 is known, right, then I can simply write A1 equals to 1 minus A2, P1 equals to 1 over 2 A2, which is also equal to Q11, right? So all of these are just rearranging what we see here. So for the midpoint method, what do you think, or for the modified Euler's method, actually? We kind of already talked about that. What would A2 be in this case? We just said it. Half, right? So if A2 is equal to half, then we get Hund's method, which is modified Euler's method. If A2 is equal to 1, what do we get? So you get 0 for A1, yeah. What's P1 and Q11? Right. So if P1 and Q11 are half, and A1 is 0, which method do we have? Midpoint method. All right, so this is the midpoint method. If A2 is equal to 2 over 3, okay, then it actually minimizes the truncation error the most. Okay, so if A2 is equal to 2 over 3, then we get a method called Ralston's method, which we haven't covered yet. But this here is the minimum bound for the truncation error. Okay, so it's better than the Hund's and the midpoint. So found to provide minimum bound on the truncation error. All right, so if A2 is equal to 2 over 3, what's A1 in this case? So the general equation is yi plus 1 equal to yi plus what? A1 K1 plus A2 K2 times H. In this case, A2 is what? 2 over 3. So it's 1 over 3. So A1 is 1 over 3. That makes 1. And then in this case, K1 is equal to still the derivative or the ODE at the initial conditions. So TIYI. What's K2 in this case? Still the derivative, right? But at TI what? P1. What's P1? NYI plus Q11 K1 times H. So what's P1 and what's Q11? Remember from this equation up here? So if this here is 2 over 3, then what's P1? Look, you have half, and this here is all right. So 3 over 4. So Q11 and P1 is 3 over 4. So obviously, I'm not going to ask you guys to derive these. Okay, we're just deriving them in class, and then we will provide these equations so you guys can use them. So we've covered this method. So now I'll give you an example, okay, to try using this method to solve for the value of y at time equals 1 second. So the problem here, I guess let me just draw a line here. So example 1, we have to find y at t equals 1 using Ralston's method, which is a second order Runge Kutta. And you're given dy by dt is equal to 4e 0.8 t minus 0.5 y. You guys recognize this? Yes. So y at t equals 0 was equal to 2, and I want to let the step size h be 1. All right, so try this out. I'll give you guys 5 minutes to try this problem out. All right, so 5 minutes are up. So I'll start trying to go through the problem. Did anyone get K1? 3. Anyone get K2? Close. It's 5.16. All right, so let's go through it. So we know that we're using Ralston's method, and to use Ralston's method, there's two unknowns, K1 and K2. So what you want to do is solve for K1 and then solve for K2, and then you can find the value at the given time step. All right, so K1 is equal to the slope, or the slope basically at the initial conditions. In this case, the initial conditions are T naught and Y naught. So T naught, Y naught, and in this case, basically the Y naught is 2. So this here is 2, and this is 0. So I plug it into the equation, the dy by dt equation. So we're going to get, this is equal to 4e 0.8 times 0 minus 0.5 times 2. So the left side is 4, the right side is 1. So we get 4 minus 1 is 3. So this is our K1. K2, using the Ralston's method, right, is a function of the derivative at t naught plus 3 over 4 h and y naught plus 3 over 4 k1 times h. So in here, this is 0, t naught is 0, that's the initial point, plus 3 over 4 times the step size, h, which is 1. So this gives us 3 over 4. Here on this side, we have y naught is 2, so this here is 2, plus 3 over 4, k1 is 3, and this is 1. So you do the math, what do we get? 4.25. So this is equal to, we're going to plug in the equation 4e 0.8 times the time, which is 3 over 4, minus 0.5 times 4.25. You do the math, this is where we get 5.163475. All right, so that's K2. Now we can solve for yi plus 1 because we have K1 and K2. So we're going to plug that in. So yi plus 1 is going to equal to yi plus 1/3 K1 plus 2/3 K2 times h. So you plug in all the values, right? We have here, this is 2, K1 is 3, K2 is what we got right here, and then h is 1. So we do the math, and we get 6.442317. The relative error here is 4%. Why? Because the true value from the previous lectures is 6.194631. Okay? So 4%, right, is half of the actual error we got from the modified Euler's method. So this is obviously, like we mentioned, is better than the Euler's method, the modified Euler's method, which is Hund's method. So the Ralston is much better, as we see here. All right, so now we're going to cover the Runge Kutta method, but the fourth order. And I'm going to just give you the equation, okay? And then we'll do an example with it. So the classical fourth order Runge Kutta method, all right? So it's yi plus 1 is equal to yi plus 1 over 6 k1 plus 2 times k2 plus 2 times k3 plus k4 times h. So you can see here that a1 is 1 over 6 and a2 is 1 over 3. All right, so k1 here is the slope, right, at the initial conditions, so ti, yi, then k2 and k3 are both at the midpoints. Okay, so this is going to be a function of ti plus a half h, and this is going to be yi plus k1 times h divided by 2. Or I could have written also half k1 times h. Here we're going to have ti plus half h and yi plus k2 in this case times h divided by 2. And then k4 will be the value of the derivative at the predicted kind of point, ti plus h and yi plus k3 times h. So you can see that every time we calculated the k value, we used it in the next value, right? So that's kind of the pattern that we see here. So this is the fourth order Runge Kutta method, very similar to the format that we've seen before, just a bit more equations. So not too complicated, I would say. So let's try an example here. So example 2. So we're going to repeat the last example, which is example 1, using classical fourth order Runge Kutta, so RK. And from the last problem, we had dy by dt equals to 4e 0.8 t minus 0.5 y. H was 1. Y at t equals 0 was 2. So, and we want to find what is y at 1, t equals 1. So just like the last method, right, we look at the equation here. The main things we need to find are k1, k2, k3, and k4. Once we find those, then we can solve for yi plus 1. So because I gave you time in the last example, so you kind of already see the idea. So we'll just go through this problem together. So we have k1 is going to equal to the derivative, or the ODE, at the initial points. So in this case, t naught and y naught. So this here is 0, and this is 2. We do the math, just like in the last problem. What do we get here? 3. So that's k1. Now we go to K2, which is at the midpoint. So now it's going to be T naught plus H divided by 2, and Y naught plus K1 times H divided by 2. So in this case, what I like to do is to figure out what these values are first, and then do the math for the actual ODE afterwards. So T naught is 0, H is 1, so this is going to equal half. Then we have Y naught plus K1, which is 3, so this is 2, this is 3, and then H is 1. So it's going to be 2 plus 3 over 2, which is going to be 3.5. So in here, we plug it into the equation. So 4e 0.8 times half minus 0.5 times y, which is 3.5. You do the math, you get 4.2173, and this is K2. Next step, K3. So K3 is also the midpoint. So we have the function here, T naught plus half H. Then we have Y naught. Instead of K1, now we're going to be using K2 times H divided by 2. Again, this part here is equal to the half. And this part here, if you do the math, you'll get 4. It's basically 2 plus K2, which is 4.2173, times H, which is 1, divided by 2. So you get a value of 4.1086494. Okay, you plug it into the equation that we see up here, right? The same equation. You do the math, you'll get a value of 3.912974. And then the last part is K4, which is going to be T naught plus H and Y naught plus K3 times H. So here we have, this is equal to what in this case? 1. And then Y naught plus K3 is going to be basically 2 plus 3.912974 times 1. So that's going to be 5.912974. So you do the math, and you get a value of 5.945677. So now we go back to that original equation, that long equation, right? Yi plus 1 is equal to 1 over, or yi plus 1 over 6, k1 plus 2 times k2 plus 2 times k3 plus k4 times h. So here h is 1, k4 is what we see up here, and then k3 is what we see up there as well. All those numbers, you plug them in, and you get a value of 6.201037. Relative error here is 0.1%. You can see that, much more accurate than what we saw earlier in the previous problem. So this is the value at y t equals 1. All right. So now I'm going to give you a bit of a challenging problem. All right. So it's going to be a system of equations. All right. So we have in this problem basically a system of equations. So two equations. We have dx by dt equals v, and dv by dt equals the gravity minus the coefficient of drag divided by mass times the velocity. And we want to use the fourth order Runge Kutta. So what we're going to have to do is step by step apply these equations k1, k2, k3, k4. But as we're going through these, just like we did in the example just now, we have to find out these intermediate steps. So what is the value at the midpoint, so we can use it in the following iteration, or the following k value. So to start off, I'm going to call this here dx by dt as f1, which is going to be a function, if we write the general form of t, x, and v. All right, so this is actually equal to what we see up here, which is just v. Then we have a second function, so dv by dt, and this is going to be f2, and also it's a function of txv. But this is equal to what we see up here, which is g minus 0.25 divided by 68.1 times v squared. We can also plug in here this gravity value, which is 9.81. So in the first step, in the Runge Kutta, we want to find what the k values are, right? So what we're going to do is go through all of them. But in this case, we're going to have two sets of k values. So we're going to have one for displacement and one for the velocity. So let's do that. So we can kind of draw a dash here or a line. So k11 is going to be for the velocity. Okay, so this, I'm using the same one here for velocity, and then for displacement, and then for velocity I'll use 2. So k11 is going to equal to f1 at what the initial conditions, right? So this would be t naught, x naught, v naught, which is equal to the velocity alone. So this is equal to v naught. But if I wanted to write all the variables in there, this would be 0, this would be 0, and this would be 0, right? So in here, we write k1 is equal to, k11 is equal to 0, right? Because it's equal to v naught, and v naught is 0. k12 is going to be the one for dv over dt. So f2, again, this is going to be 0, 0, and 0. This is going to equal to 9.81 minus 0.25 divided by 68.1 times v naught, which is 0 squared. So this is equal to 9.81. So now we have the values for k1. Now we want to go to k2. Before we go to k2, right, what we need is to find what is the displacement and what is the velocity at the midpoint. Okay, so at the midpoint, what we have is x. So now I want to remind you that h here is 2 seconds. Initial point is 0 seconds. So the midpoint would be how many seconds? 1, right? So the midpoint would be x at t equals 1. And this is going to equal to x at 0 plus, what do we have here? k11 times h divided by 2. So this is going to equal 0, because initially displacement is 0, plus k11, which is also 0, right? Times h, which is 2, divided by 2, we still have 0. Now we'll look at the velocity at time equals 1, or the midpoint. So this is going to be v naught plus k12 times h divided by 2. So v naught is still 0. k12 is 9.81 times h, which is 2 divided by 2. So this is 9.81. So now we have these midpoint points, right? And the other, midpoint would be the time, which is time equals 1. So then we go to k2. So we can draw this dashed line, I guess, here. So k2, 1, is going to equal to function 1 at what? t1, x1, v1. What are those? The midpoint, right? So this is the midpoint. This is going to be 1. This is going to be 0. And this is going to be 9.81. We know that K2 is equal to, the function 1 is dx by dt, which is equal to v, right? So this would be equal to v1, which is 9.81. K2 is going to be f2 at 1, 0, and 9.81. Again, what we do is we apply this equation up here, right? So 9.81 minus 0.25 divided by 68.1 times the velocity, 9.81 squared. You do the math, you get a value of 9.4567. So far, so good? All right. So now, again, in the Runge Kutta fourth order, the next step is to find the value at the midpoint again, right? You guys remember from here? So this is midpoint, and this is also midpoint. So what we have to do is now update the values we have at the midpoints using these new k values. Right? We have new k21 and we have a new k22. So we're going to have x at 1, which is time equals 1, equal to x naught, or x at 0, plus k21 times h divided by 2. So this is going to equal to 0 plus, we have k21 is 9.81 times h, which is 2, divided by 2. So we get 9.81. Now we have the velocity, on the other hand, v0 plus k22 h divided by 2. So here we plug in, 9.456. So it's going to equal to 0 plus 9.4567 times h, which is 2, divided by 2. So this is, again, 9.4567. So when we're going to calculate K3, right, in this function, for time, we're going to give 1, because that's the midpoint. For displacement, we're going to put 9.81. For velocity, we're going to put 9.4567. Right, so just reminding you, this is T1, X1, and V1. You apply the equation for dx by dt, which is simply the velocity. So this is going to be 9.4567. Then K32, second function, again, 1, 9.81, and 9.4567. Then we apply the bigger function, dv by dt, which is 9.81 minus 0.25 divided by 68.1 times the velocity, 9.4567 squared. So you do this math, and you get 9.4817. All right? So now we want to find, so I forgot to kind of write here. So this is at the midpoint, and this is at the midpoint also. So for K4, where do we need to find the value? We're going to use K3, okay, but it's in the endpoint, right? So these were the midpoints. So now we want to find what is x and what is v at the endpoints, right? So at the endpoint, which is going to be at 2 seconds. Why? Because h is 2 seconds, right? So that's the step size. So we're going to use x naught plus what? K31 times h. So this is going to equal 0 plus 9.4567, right, times h, which is 2. So we get a value of 18.9134. And then the velocity at 2 seconds is going to equal to the velocity initially plus k32 times h. And then this is going to be 0 plus 9.4817 times 2. This is going to equal 18.9634. Now we use these values to figure out what is K41 and K42. Okay, so K41 is going to be the initial function, which is dx by dt, right? Where the time here is going to be 2, x is going to be 18.9134, and velocity is 18.9634. You plug it in to the equation, which is the velocity only, so we just take this value, okay? Again, 18.9634. K42, on the other hand, is F2, and this is the same inputs. And in this case, we apply the larger equation, right? The gravity one, and we get a value of 8.4898. So now we have all of our k values, k1, k2, k3, k4. We can now solve for, the value of the velocity at the future endpoint. So obviously what we did here is not, the final. This is just an estimate. We're going to have 2 equations in this case, one for x and one for v. So x is going to be, this is x1, it's going to be x0 plus 1 over 6 k1 plus 2 times k2 plus 2 times k3 plus k4 times h. Okay, so in here, x0 was 0 plus 1 over 6. K1 was 0, I think. K1, 1, right? K1, 1 is 0. K2, 1 is 9.81. And you guys get the point, okay? We just plug them in, multiply by h, and then you would get the value, all right? So in this case, we can see here that, x1 would be 19.16561. So I took that directly from this table. Okay, and then v1 would be, do the same math, but to use the values in here, which are, not 1, but the 2. Okay, and what we see here is these values are all less than 0.1% error. Okay, so they're very accurate using this RK, even though the H is 2 seconds, right? So when we're looking at modeling a system, right, if you look at in engineering, if you want to model a bridge, you want to model, some type of mechanical system or electronic system, we typically mesh the system, right? Have you guys seen these, like meshes? Right, we make an object into meshes, and then we solve ODEs, step by step to find out, okay, what's the change here? What's the change there? And so on. So typically, this mesh size depends on, what's the method that you're using to solve these. And if the method is good, like the RK4, right, then you can have a large mesh size and still have a good solution. Okay. And one thing, if you get to the point where you're using mesh sizes and you want to figure out, is my mesh size good? Then what you have to do is try out a mesh size. Let's say a mesh size of 10. Then try out 8. Then try out 6. Then try out 5. And look at the trend. Let's say the x-axis is mesh size here. And this is the kind of, let's just say the value that you're solving for, okay? Whatever value, the value you're trying to solve for. You graph it. As I decrease the mesh size, maybe you're kind of getting to a value like right here. When you have a large mesh size, maybe you have a value like way up, like here somewhere. Maybe I didn't draw this perfectly actually. Let's go like this, like that. So as I decrease the mesh size like this, I'm converging to this value, right? So when you see that the change between each mesh size is not changing that much, then you know, okay, this is a good mesh size. Okay? So kind of related to the topic of solving ODEs. That's why I brought it up. All right, any questions? So that pretty much sums up the course. That's all the material I'm going to give you guys. This problem is a bit long, so probably don't expect it on a final, okay, or a quiz.